Okay. Yeah. Welcome to the second talk of today, to Introduction to Tower. It kind of struck me after I proposed this and said to Rainer, hey, I do a talk. If you don't find a second speaker, I will talk about Tower because I play around with Tower a lot. That this is basically the sequel to my other two talks that I had at Rust Linz, which were Tokio, Warp, and WebSockets, and the other one was serverless Rust. And now I'm kind of combining both. I'm having a couple of things from the Tokio ecosystem. I'm going to show you a couple of things from serverless, and I'm giving you an introduction to Tower, which is a quite interesting framework. So my name is Stefan. I'm one of the organizers of Rust Linz. This is the worst Twitter handle in the entire world. It's short for Dead Parrot. If you want to reach out or want to chat with me, that's the best way to get me usually. Quick disclaimer up front. So everything that you're going to hear today, take it with a grain of salt, because I'm not involved in the Tokio projects. I'm not involved in the Tower projects. Everything I learned and everything that I collected here was done by me. So I did a lot of research. I read a lot of documentation and looked in a lot of forums to see what was going on. Was looking in some GitHub issues, etc., to get myself an image that works for me, and it might work for you as well, and you might be able to ship great software afterwards. But it might be that I get a couple of things wrong. And up front, I'm sorry if I've done that. I'm pretty sure people in the comments are going to correct me, because that's what they do. So yeah, if you know more about that, please tell me and reach out to me. Tower is part of the Tokio stack. So we have spoken about Tokio a couple of times here in Rust Linz already, and I'm pretty sure if you've done async programming, you have seen Tokio and you have done something with Tokio. Tokio is not only a runtime for asynchronous programming, but it's also an entire ecosystem that comes with tools for network applications like Hyper, which is a complete implementation of HTTP 1 and 2. For the client and for the server, or Tonic, which is, I guess, the gRPC equivalent of Hyper. And both those layers, Hyper and Tonic, they build up on Tower. Tower is this one box in the middle here, which is basically an abstraction. It's nothing more than it. No, there's a lot more to it, but the core of it is an abstraction to abstract the request response pattern, not only for servers but also for clients. So they got rid of the server name in the abstraction and call it service. And what you can think about is it's basically middlewares. You're stacking middlewares on top of it, and you can reuse them throughout your applications, depending on which applications that you're writing. And I think it's called Tower because you have a tower of services. Again, this is just me trying to figure out how things work. But you have a tower of services that you stack upon each other. And when a request comes to your application, it first goes through the logger, then you log out some stuff, then you check, then you have a timeout check, so your request doesn't take too long. Then it's being transformed into an actual HTTP request that lands in your function, so you can work with it, you can do something with it. And then you send the response back, and there you go. Again, Tower revolves around this service trait, and it kind of looks like this. It has a couple of associated types, and it has two functions that need to be implemented. The first one is poll ready. This gives, if you're familiar with async, it gives you a poll pending or a poll ready. That's an enum that's being used in async programming, which tells you either, well, that the service can be used. I'm ready to process your service or to process your request. Or it's like, wait for a second, I'm not ready yet. I can process your request later on. This is great if you have things like queuing or load balancing or load shedding that you want to implement as a service. You can do it with this poll ready function. You can say, wait, I'm full, my buffer is full, please wait until you use me when I'm ready. And yeah, this is the same poll that you get from polling a future. The other one is call. And with call, you are getting the request object. You can work with it, and you return a future again. And most of the time, you're returning an inner future. So services are meant to be wrapped around each other like an onion. with the last one in the middle, and usually you returning the future from the last one, and then again from the inner one, from the inner one, from the inner one, until you reach the outer one. So it's a very simple trait, not that much to implement, but it can get very complex, especially if you want to compose your services later on. Let's look at the very simplified logger service. So what we want to do, we are writing an HTTP application, and what we want to do is that at the moment the request comes in, I want to log a little bit information about this request. Usually I'm creating a struct that is a generic with an inner service. So this is the wrapping, that this is how you build up your tower, just services within services. And this is also everything that that logger is doing. So you are just taking another service, you own it, and you compose it. It gets interesting the moment you have the service trait. So here we are implementing the service for HTTP requests with a body for the logger. So this is how we implement the service. And this service, we're implementing it for other services that can handle requests. So I'm talking a little bit more about this in just a second. Since we get requests in and push requests down, we also get responses up. This is what's happening here. And if an error occurs, we're just bubbling up the error from the other service. The return future that we expect, the future that's being called afterwards when everything's wrapped up, is also the future from the service that we wrap. So basically, we're taking everything from this one service. The polling function polls the inner service, so we know if the inner service is ready. And here, that's everything that we do. So the moment this service is called, we say, well, we are processing whatever method at whatever URI, and call the inner service. You see, this is an expression, so there's no semicolon in it, which means the inner service is also returning a future. And there you go, everything's wrapped up. This is how a service should work in theory. Not only in theory, this actually works also in production. I've used this a couple of times. It's probably not the best service, and you can do much, much better things with it. But for a hello world, it's nice enough. Let's look at those services in detail. And let's look at those services by implementing an application that should run both on AWS Lambda and Azure Functions. So I want to create an application that is totally independent from the environment where it's running. But I can have a layer that adds my application either to an AWS Lambda invocation or to an Azure Functions server. If you've seen my talk Serverless Rust, I talk a lot about how those different serverless architectures work. Lambda is very special in how it's being invoked and how it gets its tasks. And Azure Functions, which is very, very nice if you want to migrate your app to Azure Functions, is basically a server with some boilerplate code. So it's not entirely true for all of Azure Functions, but if you're doing Rust on Azure Functions, you are just providing an HTTP server and hook it up to the function host, and there you go. Which makes basically every one of your HTTP applications also a fully qualified Azure Functions application, which is nice. The app, as you can see, there's no sign of anything async other than the async keyword here, or anything related to Tower or Tokio. What I have here is I have a handler function. It gets in an event. So this is the payload that I want to deal with. I wrapped the third value inside this tuple struct. I don't know why anymore. I guess you just can pass the value itself. That should work also. But I call it event mainly because of the naming. I extract the value here. I see if the first name is here, and I want to say either hello Stefan or hello world or whatever, and also put a value back. So the value is also the result that's being pushed up. That's like you would expect to write a serverless function. I have an error. It's a boxed error. It's that I can consume every error, and it has one dependency on 30. That's everything it is. And I want to take this function and attach it to AWS Lambda and to Azure Functions. For Lambda, I'm writing a Lambda Event parser, which is a service. It takes an inner service via generic. So the constructor, the implementation of of my struct looks like the one from the logger. That's basically, I guess you can create a macro for that. That should work as well. I don't have any other things that I need to wire up here. It gets interesting once we implement the service trait to it. So this is the entire implementation. It still fits on a slide, which is nice. Let us go through a couple of things there. First, I implement the tower service for Lambda events that carry a 30 value. So this is one generic that I need to fill out. I'm implementing the service. If a Lambda event with a 30 value comes in, then this implementation is valid. And this is what's incoming, and this is what's outgoing. So if you still think as this tower of middlewares, this is what's coming from above and going down to your own function. So I want to convert a Lambda event that carries a value to a service that can carry an event. And this event type is this one type that I defined in my function. You know, this one thing that a tuple struct with a 30 value. Very similar to the Lambda event, but with less fields and much easier, and none of that Lambda has. So that's that. Since I'm working with values here, both in Lambda and in my service, I can just bubble up the response types and the error types and the future. That's all fine. I don't need to do anything here. So the response will be a 30 value, and Lambda can work with 30 values. Great. And also the error, it's the any error anyway. Bubble it up. That's fine. Now for the call function, it's pretty straightforward as well. I get the request. I split it into parts. That's a function from the Lambda event. I'm taking this value. This is now the value, like the 30 value, wrap it into the event and call the inner service. The inner service returns a future. This is the future node that we defined here, the type future as : future. Give it back. And that's how we integrated our function to Lambda. Now for Azure Functions. I'm writing an HTTP parser because it's not only for Azure Functions, but basically for every HTTP server, which is nice. Same thing. Again, I could possibly write a macro. I wrap a service inside the HTTP parser. However, it gets much more interesting when I look at the types that I need for implementing the service. So I'm implementing a service for an HTTP request with a body. So this is all from Hyper, from the Hyper crate. Where? So this is again incoming. This is there's an HTTP request with a body incoming to your service. Now please unwrap it. And I want to send it, this line, to again a service that swallows my events, that takes those events that I have defined within the app, which is Sun's implementation detail. I need to define a couple of more trait bounds because hey, we are in an HTTP server. Futures need to be sent across multiple threads, possibly. If you are sending those futures across threads, then maybe you want to have static lifetimes, which is typically for HTTP servers. I guess Rainer mentioned something like that in his Rocket talk from a couple of years ago, actually. So yeah, I needs a couple of trait bounds to work, but that's it. You're getting lots of error messages if you don't have those trait bounds. So we'll know. So also the future from this service needs to be sent. And I guess the response just needs to have debug and display because I have a couple of log lines in there that I want to use. So this is all related to the service that I want to call. So coming from the HTTP service, this is the next one. The types, the associated types are also very different. So the response now is not just what comes from my own function, from my own handler function. Since I'm in HTTP land, I need to provide an HTTP response with the body again. So this is a type that comes now from Hyper. And it's my duty in this layer that I wrap what's coming from this service to produce a response, an HTTP response with the body. The error is the same. I guess in this implementation, I just use the anyhow error instead of writing it on my own. But I can use the same error. And here I have a future, which is a boxed future with static lifetime and the result again. So this is a little bit long. I'm going to tell you in a second why I need a boxed future. Because I want to do a couple of things with the response that can't be done as easily as we've seen in the last example. So I need a boxed future. I'm going to tell you in just a second. It's very important to get those types right. Those types will make or break your entire implementation, and you are getting error messages from hell. So this is if you're getting one trait bound wrong. I guess here I forgot the send trait, the send trait marker to add as a trait bound. Then you're getting towered, which means you're getting pages of error messages with all the generic jazz, and especially if you're wrapping things into each other. It's generics and generics and generics and generics, and one little implementation might not work. Boom, that's it. I hope that those error messages will get a lot better to read the moment we have async traits within the language. So especially all the boxing and pinning, I guess, will be easier because we're not only trying to return futures, but we can say, well, this is an async function that returns a result, and we can get the future terminology out of it, and that should already make it easier. So hopefully, Nick Cameron was at Rust Linz and spoke about that, and I asked him this question. He said, yes, that should be easier, hopefully. So really looking forward to what the async working group is doing. Alrighty, let's look at the implementation, at the call function. Here are a couple of things that are very, very different. What we want to do is we want to call the service somewhere within our code, take the result, and then produce an HTTP response. And because we are calling this asynchronous function somewhere in the middle, we need to create a future that doesn't move in memory anymore. This is what the box pin does. This is, I guess, a talk entirely on its own, and I guess Without Boats did one at one of the Rust comps, which you can find in the Rust channel, all about pinning and boxes. We're not doing this here today. Just know we are doing all the jazz and having boxed futures and boxed pin, etc., to be able to do something before we call the inner service and to do something after we call the inner service. This is why we are doing that. First, we are cloning the inner service. Clones are pretty cheap. You don't clone that much. So memory-wise, it's not that big of an operation. But the problem is that your async, so your future might already be polled when the clone is not ready yet. This is something that I've read in the documentation just recently, which means that this line here, make sure that your clone is ready by replacing the clone with, or the actual inner service with the clone, and then you can work on the actual inner service. That's just this technique to make sure that the clone is ready and that you can work on it. Then we are pinning, so we are creating an async block. We are pinning it in memory so that it can't move anymore. We prepare the request. So this is the request object, which is an actual HTTP request. What this function does is that it extracts all the information that we need and puts it in some data, which is assert a value again. Then we call the inner service, wrapping the assert a value in our event structure again, await that. And once you get the result, either if the result is okay, I'm going to return an HTTP response with a status code okay, and with the result a string. Otherwise, an empty body and an internal server error, so that we can have two different responses that are okay but carry the error value inside the response and not with the Rust error, something like that. And that's the implementation to attach my function to an HTTP server and ultimately to Azure Functions. Okay, that's the implementation of a service. We can use the service, then we can wrap our services within each other, that's fine. Or what's much nicer is to create layers. Layers are data structure that work next to services, and you can chain them. So you can say, well, this layer, then this layer, then this layer, then this layer, just like you would have a middleware stack. We are going to see an example just recently, just in a couple of seconds. The implementation is also very similar to all the others. Here we are creating the new service, wrap the inner one via these layer functions. You just need to implement the layer function. The structs can be empty, so there's nothing much to it. And this is for the HTTP parser. This is for the Lambda Event parser, same thing, different names. So just wrapping your service in the Lambda Event parser. Okay, how are we going to use that? This is how it's being used in Lambda. They just updated the SDK. They now provide you with a service function, which means that you can take your function and wrap it into a Tower service. So now it's compatible with Tower, with the interfaces that you defined. This is a very nice way to make every one of your functions Tower ready. Then we create a new service builder. First layer is a timeout layer. I don't want my function to run longer than 3 minutes. And I'm using a timeout layer here and the timeout service here because I want my implementations on Azure Functions and Lambda to work similar. And in Lambda, I can configure a timeout per invocation. And I guess I can't do that with an HTTP server in Azure Functions. I want them to work similar. This is why I use the timeout layer here. Then I have my Lambda event layer, and then I have my function. And I run it. That's it. So this is being wrapped into a service, and the Lambda event layer takes what comes from above, which is a Lambda event, transforms it into something that the function can read, and then we bubble the values up again, and we're done. Fantastic. This is how we are doing it in Azure Functions. We are creating an HTTP server. I'm using here Hyper. I'm not using a framework, just Hyper as it is. I have a port key, the function is custom handler port. I let it listen on localhost. So this is you have to listen to this port if you want to attach it to Azure Functions. This is how the function host is communicating with your server then. Spin up a server. And again, I'm also building up a couple of layers. So I have this make service function, which is a constructor, a factory, services, the service for services, or a service made out of services. I have the service builder again, the same timeout layer. I even included a log layer because I wanted to have some log output. Then my HTTP parser layer, and then again the service function, just like in the other example, with my handler function. And there you go. Boot up the server and serve all my services, and that's it. So the cool thing is everything here with the service builder and my service function, that's all the same thing, no matter if I'm on Azure Functions or if I'm on AWS Lambda. The only thing that I need to change is the HTTP parser layer for Azure Functions and the Lambda layer for AWS Lambda. And then my app works on both serverless architectures. Fantastic. This is what I wanted to achieve. Cool. And that's that. So what's in the box with Tower services? It's not only the trait, it's not only the service trait that you can implement. There are a couple of things in there that are really, really important if you want to create networking applications, especially if you think about Kubernetes and Kubernetes clusters. I guess the Istio service mesh, if I'm not mistaken, uses Tower a lot to implement all the networking connections that go between your Kubernetes pods. And you can do things, that help you for an HTTP server, for example, like having timeouts or logging, request limiting, buffering, throttling, but also you can have stuff like load balancing, load shedding, etc. I work at the monitoring company. What I created a little layer that produces open telemetry spans, so I can have for all my requests a little bit of default telemetry already hooked up to our monitoring solution. I just need to include this one layer and I'm done with it and get at least some monitoring. So that was really nice. As for the ecosystem, Hyper is based on Tower. So I guess even the whole Tower concept originated from Hyper, if I'm not mistaken, because I could see things like the make service function and the service function first in Hyper, then in Tower. So now you're using Tower directly. And yeah, if you spin up a Hyper server or Hyper client, you are creating services that are based on Tower. So since Hyper is based on Tower, so it's every web framework that is based on Hyper. Guess what? And in some, you can see that, for example, Exum. So Exum makes really, really good use of Tokio of Tower services. They are not hidden. You can see them and you can add just layers as you like. If we have a little bit of time, I'm going to show you a little example there. So yeah. If you're saying Hyper applications or Hyper-based applications, you're basically saying Tower anyway, which means if you have a set of really nice reusable services, which are probably very generic, then you are good to go for every Hyper application that you're doing. A couple of things to read. I have a couple of examples that you can find on GitHub. I would also invite you to read the Tokio blog about inventing the service trade. This is a blog article that was released last year, which really shows why the service trade is important and why it is like it is. And you can find all the slides and all the information that you see here today tomorrow on my blog, or if you're watching the video on the Rust channel, it's already there. So I'm definitely putting up the slides before I'm putting up the videos. Okay. Do we have a couple of more minutes? Because then I have another example. I just want to click through so that you know how a timeout service, for example, is implemented. And I'm going.
Stefan, I think you are good to go. It's super interesting, and I think many people will be happy to see some examples.
Cool, great. So I'm going to boot up another application. Give me just a second. Boom, boom, boom. So, and there you go. Alrighty. So let me move it around. Let me make it a little bit bigger. No, that's the wrong one. I'm super sorry. I have 7 VS Code windows open, so and all look rusty. It's that one. It should be that one. Okay. Yeah. Okay. Now I need to find it here. Okay. Let's make it a little bit bigger. So what I did here, I created an Exum server. I don't know if we've done Exum on this channel already, but we should. So it's a fantastic new framework, I think, and maybe we can get some of the core team, because I guess somebody from Denmark develops on Exum. This would be very interesting for Rust Linz. I can define a couple of routes, and then I'm going to, I have a couple of get handlers here, where I say the root uses this handler, the timeout, I'm taking this timeout variable, and it goes into the timeout handler. And the idea is that I have, where's the timeout handler? It's here that I sleep for the number of milliseconds that I get in. So if I'm saying localhost /1000, I'm waiting 1000 milliseconds. Localhost /100, I'm waiting 100 milliseconds, stuff like that. And if this number of milliseconds is lower than my timeout limit, then I'm writing out I made it. But here I have, those are my routes, and then I'm having a logger layer. Again, I want to log my stuff, and I'm having a timeout layer that waits for 300 milliseconds, which means after 300 milliseconds, this future resolves, this future is in poll ready, which means that the entire service is in poll ready, which means that the actual future from the timeout path is being cancelled. And I'm handling the error in here. And so if I curl it with, let's say, 500, you can see here, it's processing get 500, and it's an elapsed error, so it's canceling the error. If I say, let's do 100, here I'm getting made it, and my logger also said, well, I'm processing it, and it has been processed afterwards. So this is how it should work. Let's look at the timeout layer. This is the timeout layer. The same thing. It's wrapping the timeout service. So this is what it does. But it has another parameter, which is the timeout itself, which is a duration. Let's go into the timeout service. It has the inner service. It has timeout as duration. Couple of constructor functions, conversion functions. And this is the whole implementation. And you can see it needs to work on requests. Fantastic. It has the errors. This is nice. You can use any error that you like, as long as it can be converted into the box error from this trade. This is a very nice pattern. So this makes compatibility pretty great. If you say the only thing that I need to provide is something that can be converted into the actual error, instead of trying to align all your errors or all your results. I have the poll ready. It's either in pending or it's in ready. If I have an error, it's being mapped. And here's the call. So I have two futures. One is the response if I call inner. the other one is the sleep future, and then I'm putting both into the response future. Going into the response future, if I'm looking at the poll, the only thing that it does is, well, let's see if the actual future is ready, if the actual request is ready, then check the sleep function. And yeah, if it's ready, then return an error because, well, the timeout has happened, the timeout has elapsed, and the other one is just being cancelled. So this is what happens here. And that's not that much of code. So it's a couple of lines with arguably some async magic that you need to get used to. But with that and this great abstraction of a service that takes stuff from above and puts it down to the next one, you can really compose fantastic network applications with it. So yeah, and that's about it.